Hello everyone. So today we are going to take a look at this interesting problem, right? So we are given an array of numbers like this. Let's say we are given some array of numbers, whatever. It does not have to be sorted, all distinct. So let's just change this to something like 100, right? Assume all are distinct. Okay. And you have these constraints. So if you just look into every coding challenges in LeetCode or Codeforces, right? So it's always a good idea to take a look at the constraints. The size of the array, let's say that n, it will be in the order of 10 to the power 5, right? So it means our program should run whether it O of n or O of n log n. This is a requirement. So only if we can come up with such an algorithm, we should be able to run our code within the time constraints. Okay, but let's look at the problem. We have an array of numbers, and we have to consider all possible pair of numbers, so that their for every pair we are supposed to find the XOR, right? So and the XOR, we want to find the pair which has the minimum XOR. So that's our goal. Okay, that's the minimum XOR possible given taken in any pairs, right? So let's consider the all possibilities, right? All possibilities through brute force. Okay, so we take all distinct pairs, right? Distinct pairs means let's name our array, right, as A. So we want to look at AI XOR of AJ such that I is less than J. Okay, we need to maintain this condition, right? So I mean, if you take the same if you take the XOR of same number, right? For example, why this constraint is required? Because if you take 5 XOR 5, it will automatically be 0, right? The problem will be too easy. It doesn't matter what array we get, we just return 0, right? That will be the minimum XOR if we can take the same number twice. But here that possibility is not there, so we have some interesting problem. Okay, but obviously generating all possible pairs is how many number of pairs are there given an array of n elements, which will be 10 n c2, right? N choose 2, and this will evaluate 2n into n minus 1 divided by 2, and this is like approximately equal to, given 10 to the power 5, this will be approximately equal to 10 to the power 10 divided by 2, so which will be 5 into 10 to the power 9 kind of operations, right? And this is not very efficient. Okay, so if we run this algorithm, this will certainly fail. Okay, fail in the time constraint, right? So how can we simplify the process? So before simplifying the process, let's consider some examples of the properties of XOR. Okay, so the number 5 can be written in binary form, right? So we are talking about XOR in the sense we are doing bitwise operation. So what is the binary form of 5, which will be 101? So what is the binary representation of, let's say, 8? Will be 1000. Okay, if we take the XOR of these two values, let me just write it this way so that it's clear, right? So if we take the XOR of two values, let's evaluate let's evaluate this side first, right? So XOR of 0 and 1 is 1, and we get all ones, right? Yeah, this is 1 0. XOR of 0 and 0 is still 0, so 0 is the identity element of XOR. Why 0 is the identity element of XOR? So because 1 XOR 0 is equal to 1, and you have this property of 0 XOR 0 is also equal to 1, right? And you have this commutative property also, nice commutative property also. Okay, so this is the XOR notation, right? So what is this binary number 1101, which will be nothing but 1 plus 4 5 plus 8 13. Okay, so how did I evaluate this? I will explain that exactly, okay, later. So observe this. So this will be the least significant bit, right? And this is the most significant bit of 13. For 8 is also, this is the most significant bit. For 5, the most significant bit is this one. All right, okay. Now what we can do, we can analyze these things in all right. So let's try to understand how these bits behave, right? So how these bits of like zeros and ones gives rise to the number. I mean, because obviously we want to find the minimum value, right? We want to find the, I mean, x or y will result in a number, right? And every number is represented in binary format. So that's this leading bit, so this contributes, sorry, let's look at the least significant bit here, the bit at position 0, right? I mean, let me just write it this way: the bit at position 0, the one bit, the set bit at position 0, right? Set bit at 0, it contributes how much? It contributes 1 to the total sum of the number. Okay, similarly set bit at 1, it contributes 2 to the final number. Similarly set bit at this 1 2 3 4, fourth one, right? So set bit at 4, it contributes 2 to the power 4, which is nothing but 16. So the final result should be 319. All right, so we want to look at pairs such that it cancel out the bits in the most significant part. So that's why this bit is called the most significant bit, because it is adding so much value to the number, that the decimal number that we are trying to evaluate. Okay, so we have to pair the numbers in such a way that the most significant bits are getting cancelled out. Okay, we cannot assume something like this, right? So for example, what are the heuristics we have to solve this problem? If we take two very small numbers, can we get a smaller XOR value? So that's a good question to ask, right? Let's look at some examples here. For example, consider the number let's say 5 and 8 here, right? So 5 and 8 resulted in 13. But let's take very big numbers, right? So very big, somewhat big numbers, like, so this is all ones. So this will be, the value of this will be something like 1 plus 2 3 7 15 plus 31. So this will be 31, but let's take this one. Okay, all ones but at the end 0, so this will be 30. If we take the XOR of these two values, what we will get? We will get just 1, which is such a small number, right? So we cannot assume that if we take the pair of two small numbers, we will get the minimum XOR value. That's not the case. Sometimes if we look into somewhat bigger numbers, we can get much smaller value. All right. Okay. So now let's think about it in some little bit abstract way. Assume that we have three numbers, x, y, and z, right? And they satisfy this constraint, right? X is less than y and y is less than z, right? I'm going to make a claim here. Okay, let me make a claim here. The claim is x XOR of y, sorry, x XOR of z will be less than or equal to y XOR of z. Okay, so how did I make this claim, right? So now to understand this, we have to visualize the binary format of these numbers. Okay, and especially we are particularly interested in the most significant bit, MSB meaning most significant bit. Let's say that MSB of x is equal to a, and MSB of y is equal to b, and MSB of z is equal to c, right? So if we have the, and we can easily see that a should be less than or equal to b should be less than or equal to c. All right, so this condition should be satisfied, right? Because we have x is less than y is less than z. So why this is satisfied? Let's take a very small example. So this 111 will evaluate to the 0, 111 will evaluate to 7, right? And 1 0 or 000, all zeros will evaluate to 8. So the most significant bit is important, right? So this adds so much weightage to the final number. So yes, so because of this we can easily make this claim. Okay, now consider this numbers being laid out in terms of in a binary bit representation. Like assume that they are represented as some string format. So x of a, it means it just gives us the most significant bit of a, so which should be 1, right? Because we have assumed this, we have made this claim. Okay, all right. And yes, so I mean, of course, a most significant bit of 0 is undefined, right? Because 0 does not have any significant bits. But let's just stick to this discussion. Okay, now I'm making yet another claim. X of c should be less than or equal to y of c should be less than or equal to z of c. I mean, there is a possibility that all three of them can be equal, right? So one such example will be, let's consider 3-bit scenarios: 111, 110, and 100. So yes, so 100 will be x, 110 will be, so 110 will be y, and 111 will be z. So in this, if you observe, all the significant bits are equal. Okay. All right. So this possibility exists. The all equality possibility exists. So in that case, what we will do, we will just decrement the value of this c, and we will look at the next significant bit, right? Something below the next significant bit, and that also should satisfy this property, right? So we mean this is kind of like an algorithmic proof. So if we look at the particular bit at position c, and if we decide that okay, x of c is less than y of c is less than or equal to, so if at some point if we can get to this conclusion, right? At some point if we reach this conclusion, we can clearly see that x of c XOR of z of c will be 1, right? Because we have the strict less than things. So in this example, we can clearly see that in this example which I described here, we can clearly see that x of c is just nothing but 2, right? Because we are counting from 0 based indexes. So x of 2 is equal to y of 2 is equal to z of 2. All of them are equal to 1. Okay. All right. So that's one example. But as we can see, if you look into the second bit, bit at position 1, both z and y, they have set bits 1, but x have set bit 0. Okay, so this clearly states that x of 1 XOR of z of 1 is equal to 1, which is strictly greater than y of 1 XOR of z of 1. Okay, and from this example we can clearly see why this claim should hold true, right? So the claim is that, can we find a bit position where let's say, I mean, can we find a bit position I where x of I is equal to 0 and y of I is equal to 1. Y of I can be 0 or 1. Basically, this is a question that we are asking, right? whether x of I is equal to 0 and z of I is equal to 1, and y of I is also equal to 1. Okay, and we want to find bit position. This bit position we have a specific constraint, right? The bit position, basically the maximum bit position I where this condition holds true. So if we can find that I, this claim is true. And because x is less than y and y is less than z, such a bit should exist. Okay, so if we the proof is just by assuming by induction, like assuming by induction on the maximum bit c, we can easily prove it. Okay, anyway, how to solve this problem? To solve this problem, we just sort the array. Alright, once it is sorted, we just look into the adjacent pairs, right? So we just loop from index 0 to n minus 1, n minus 2. We don't want to look into n minus 1, right? Because we are going to consider the adjacent pairs, right? So loop from index 0 to n minus 2, let's say using variable I, and we just take the XOR of ai and ai plus 1. Okay, let's say that we just set the maximum value, the minimum value, let's say set it to infinity, right? Some very really big number. Okay, and if this value is less than m, right? This is less than m, just update the m to this particular update this m to this particular value. That's it. Okay, and after the end of the loop, this m should have the minimum XOR value because of this claim, right? Because of this claim that we have here. Okay, and that's it, guys. That's a proof. I hope this helps. Alright, so if you need any one-to-one session or any help, please contact me, message me in comments, or contact me via my email or LinkedIn. I will be happy to help. Okay, have a nice day.